So, welcome back. Today I was going to finish what we're going to cover in Chapter 7. I think I'll mostly finish it here. So, the idea is that we have a couple more things to talk about before moving on. The main things that I wanted to discuss, so there's a couple special topics in Chapter 7 I'm not really actually, I guess there's really like one thing I'm not going to get into, or two things I'm not going to get into that much, which has to do with um, the finite transformation group stuff that is going on in the last couple sections of Chapter 7. I'm not going to get into that. I might have time to come back to it later, but anyway, so we'll be moving on to Chapter 8, the very last chapter of the textbook. After today, and so since there's not going to be a lecture on Wednesday, that means we'll do this after break. So I'll be sending announcements, basically telling you what else is coming in the class. There'll be like I guess it's like 2 weeks and 1 day is what's left in the class. So after today's lecture, I think it's 7 more lectures, and that's it. So anyway. So where I left off last time was concerning the isometry group of the spheres, or of the sphere. So we're thinking of unit sphere and sitting in R3. So the rotation group of the sphere, S2, is going to be what is called a subgroup. So as I mentioned, a subgroup of a group in the formal sense is a subset of the group that is a group in its own right with respect to those same binary operation. So if you have a group that satisfies all the group rules, then being a subgroup just means it's a subset that also satisfies those same rules with respect to that exact same binary operation, and of course it's closed with respect to the subgroup. So if you have two elements of the subgroup and you star them, right, you multiply them together, you get another element in the subgroup. So that has to be closed in that sense, which you get from saying that it's a group in its own right. Okay. So what is the rotation group of S2? This arises as a subgroup of the group of isometries of S2. So we have so isom of S2, this is the group of isometries. So this is a group of isometries of S2. Maybe I'll just write isometries of S2. Then what is isom plus of S2? So this is actually the isometries of S2 that are products of an even number of reflections. So recall from last time that the S2 had, the sphere had a 3 reflections theorem in the same way that R2 did, so that any isometry of the sphere was a product of 3 reflections in the way that we talked about previously. And so similarly to the exact same, so this analogy is exactly the same thing that we did, right, when we talked about the isometries of R2 and the orientation preserving isometries of R2. Right, the way that we defined isom plus here was that it was the isometries that were an even number of, they were products of an even number of reflections. Okay, and so these are the orientation preserving ones. So these are the orientation preserving isometries of S2. Okay, and so they fulfill that same role, but there's something that's different about them from when we talked about these things. So when we talked about these things, if I had just asked you to come up with, off the top of your head, some orientation preserving isometries of the plane, one of the first examples you might come up with is translation, right? So translations were included here because if you translate something, you're not thinking intuitively about what orientation is. If you translate something, you're definitely not you're definitely not changing the orientation in that sense. And so so translations are included here, but translations are not included here, right? In fact, you're not translating the sphere here, right? The sphere is being fixed. So this includes no translations. It only includes rotations, right? And so this so note, this only includes rotation. So this only includes rotations. Okay. Well, question, how do we know this? So how do we know this? Well, we have to think carefully for a second. So we already know that a product of any two reflections is a rotation, right? And so we know that it includes some rotations. But to say that it only includes rotations, this is the key. This is the trick, right? So we know it includes rotations just because we know that the product of two reflections is a rotation. But how do we know that it only includes rotations? Well, so the answer here is, since we already know that the product of two reflections, so these are reflections in S2, right? So the product of two reflections yields a rotation. In order to be done, what do we need to show? We need to show that the product of any even number of reflections is a rotation, right? But because we know this, what do we need to say? Well, if we can show that the product of any two rotations is a rotation, so if we can show that the product of any two rotations is a rotation, then what do we have? Well, then we know that the product of any even number of reflections is a rotation. Right, then we know that the product of any even number of reflections is a rotation. So any even number of reflections is a rotation. Okay. All right. So I want to show this fact. So if we can show that the product of any two rotations is a rotation, then I get that this isom plus of S2 only consists of rotations, right? So everything in here is a rotation, right? And any rotation is included there. Okay, so that's what I really want to prove. So I want to show that the product of rotations is a rotation. So the product of rotations of S2 is a rotation of S2. This is what I'm proving. So proof. So the picture can be a little tricky. So I'm going to write some of the terms and then I'll show you the picture so that you can actually see what's going on here. So suppose I have two rotations of S2. Okay, so my two rotations, the first one is a rotation through an angle theta. So this is a rotation through an angle theta about a point P on S2. Okay. But what do we mean when we say a rotation through an angle theta about a point? So we have to, I mentioned this last time, but I'll remind what it is that you actually do here to rotate, what it means to rotate some angle amount about a point on the sphere. It means that is a rotation with axis through P and its antipodal point minus P. So minus P is the notation we use when we're discussing the antipodal point on the sphere to P. Okay. All right, so that's our first rotation. Our second rotation is a rotation through angle phi about another point, right? So a rotation through an angle phi about a point Q. Okay, so there's our two rotations. That's the setup. Okay, now we know already that, say, a rotation through theta about P is the product of reflections in great circles through P. So this is a product of reflections in lines, that is great circles, through P. Okay. But actually, the lines in question can actually be any of these lines so long as it agrees with the angle value, right? So the idea, so thus, or maybe I should say in addition, okay, they can be any lines through P, say lines L and M, so long as the angle between them is theta over 2. So long as the angle between them is theta over 2. Okay. Why is this important? Well, if I give you a preview of what the picture looks like here. The reason this is important is because if I'm considering a rotation about a point P through some angle, I want to be able to link this rotation at P and the rotation that's occurring at Q. And the way that I'm going to link them is I'm going to choose these lines L and M in such a way that M is the great circle connecting P and Q, right? So without noticing that, I might get a little stuck here because it seems like these rotations are happening independently. It seems like I have no way of actually connecting these two together. And the way that I do this is in this way, where I say, oh, well, this rotation, right, viewing it as a product of reflections, it actually doesn't matter which L and M I pick here, so long as the angle between the L and M is theta over 2. So long as we have that, we're good to go in terms of the choice of reflections about these great circles. And so why don't we pick a setting, or why don't we pick, a situation where this M is a great circle connecting P and Q, right? Since we can pick it to be anything, we don't really care. So that's the idea. Okay, that's where this is headed. Okay, all right, and so that's why we pick this M. So thus we choose M to be the great circle, or the line. All right, so we can take the line M to be the one through P and Q. P and Q. Okay. Okay, and similarly, same is true for the rotation. About Q. The lines we choose are going to be called M and say N, right? So choose lines M from the first part and N, right? Having angle phi over 2. Okay, this is the idea. All right. So that's the setup. Now the actual computation is pretty quick. So let r bar sub m, or r bar sub l, and r bar sub m, and r bar sub n be exactly what you think they are. Let these be the reflections through those lines. So let these denote the reflections through L, M, and N, respectively. Okay. Then the rotation through P, or I should say through angle theta about P. That is, we said that was reflection in L and then M, right? So this is written left to right. This would be R bar M times R bar L. Right, so the reflection in L happens first. Okay, and rotation through phi about the point Q is M is the first one and N is the second. And so written left to right, this is R bar N times R bar M. Okay. So remember the occurrence here, this is function composition, right? It's always tricky. This is function composition, and so if you're thinking about how this acts on your space, then it's acting from right to left, so the one that's written on the right acts first, right? So this would be reflection through L, then reflection through M. That would be this product. This would be reflection through or across M, and then reflection across N. Okay, so that's how this works. Thus, their product is following. So thus their product is well, it is I do this rotation and then I do the second rotation, right? So I have this written, and then to the left of that I have this second rotation written. So written left to right, this is R bar N, R bar M, R bar M, R bar L. But reflecting through M twice in a row, that's just the identity. And so this is actually R bar N, R bar L. Right. So this is a rotation. And so we've shown that the product of any two rotations is a rotation. Now, I have this statement, this is a rotation, we're done. But you look at that and you say, wait, why do I know that's a rotation? So to see that this is actually the rotation, let's again look at this picture. Why can we say that this thing, well, let me zoom in again. So why can we say that this thing written here is a rotation? It's not either of the rotations that showed up here, the rotation 1 or rotation 2. It's something else. It's a so it's a reflection across the line L and then a reflection across the line N. How can I view this as a rotation? So here's where the picture comes in. Consider where L and N intersect. Okay. The lines L and N intersect at some point, labeled R here in this diagram. That reflection is just the one that reflects across L and then across N is a rotation through this angle, right? Whatever angle these L and N meet at, it's a reflection, or it's a rotation through that angle about the point R, which is the point of intersection of those two lines. Okay. All right. And so, indeed, there's nothing funky going on here. If I restrict my attention to an even number, or to isometries that are a product of an even number of reflections, what I get are only rotations. So I get no translations, I get only rotations, and in fact, that's it, right? Every rotation is an example of one, and it contains only rotations. Okay. Now, what is another idea here? What is something that I want to mention kind of before going on? So there are some special rotations I want to consider. Some special rotations of S2. And we're also going to see how, in general, we can talk about space rotations in what is by far the most convenient way to talk about them. You may be getting a feel now that space rotations are very easy to talk about in the plane, but rotations in space are a lot more complicated because there's a lot more ways to rotate, right? There's a lot more room to rotate. And you might have first kind of encountered this when you thought of say spherical coordinates. Right, if you think of spherical coordinates coming from like Calc 3 or wherever you first encountered them, then this is kind of encoded in that there's just more ways to rotate in space. So so you have to be careful how these things are considered. Anyway, what are these special rotations I want to think about? So one is there's a reason why I've used the notation S2. Yes, it's a two-dimensional sphere. I can talk about S3, S4, S5 that are higher dimensional spheres, but I'm not going to. But I can talk about S1, which is the one-dimensional sphere. But you already know what the one-dimensional sphere is in R2. So this is the one-dimensional sphere in R2. What is this? Of course, this is unit circle. Can be viewed as unit circle, right? Of course, if you can alter the radius of your sphere if you care. But whenever S1, S2, whenever this notation is used, it's taken to be the unit sphere in that dimension. Okay, and so if we think about the unit circle, there's a question. What is the rotation group of the circle? So what's the rotation group of the circle? So this should be easier, right? Intuitively, this should be easier than thinking about the rotation group of the sphere, because the rotation group of the circle is the circle is an easier object. There's not nearly as much space, and so what is the rotation group of the circle? Well, to think about this, what are the rotations of unit circle sitting in R2, right? So what is this? Well, the rotations are products of reflections and lines through the origin, right? So note the rotations are easily seen to be, right? Reflections across lines through the origin. Okay. So then, what's the idea here? The idea is that each rotation of S1 can be thought of as corresponding to a point on S1. How so? How does that work? Well, the idea I'm not going to use my compass here. You're just going to have to deal with an ugly circle. The idea is, if I think of S1 sitting in R2 like this, pick a point, right? The way that I determine a reflection from that point is that I just draw the line connecting this point and the origin. All right. Now I have a reflection line. I can do that similarly for any point I like, right? Any of these points, I can draw the line determined by those points and the origin. I get a reflection line. And so every single rotation, so every rotation corresponds to a point, but how do I get, so you might say, wait, but I need two reflections here, right? But each rotation is determined by the point to which it sends a specific point, say 1, 0, right? One of the standard basis vectors. Okay, and so really the rotation is determined by an angle, right? Which is the angle between the initial and final positions. Okay, so then what I'm really concerned with here is angle, but the angle in question is between initial and final positions. And so each point corresponds to an angle. All right. But each point is really a rotation here. So each rotation corresponds to an angle, i.e. the angle between initial and terminal position. After the rotation has happened. Okay. And that's the initial and final positions of any line through the origin. Okay. What we can consider is where the point 1, 0 is sent. Right. This might jog your memory from linear algebra, where to determine the map, to determine a matrix, a standard matrix for the map, you considered where basis vectors were sent. But here, because the space in question is actually just the circle, all we need to know is where this point is, and we don't care about the other because this is one-dimensional. Okay, also, these rotations commute. Right, so these rotations commute. Because if I rotate through theta and then rotate through phi, then, so rotation through theta, then through phi, is the same as rotation through theta plus phi, or phi plus theta. And I can reverse those, right? So because that addition is commutative, well, now I can just read this backwards, right? Okay. All right, but in S2, a rotation is not determined by a point or one number. It depends on three numbers. So a rotation is determined by three numbers. Okay. So those three numbers are two angles that give the direction of its axis and the amount of turn about this axis. So two angles that give the axis, and one more to describe the turn about the axis. All right. Why is this a problem? Well, a point on S2 is parameterized by two real numbers, right? It's a two-dimensional space, but describing rotation requires three. Okay, so this is no good. It means that these can't correspond to points of S2. So because of this, rotations can't correspond to actual points on S2. Okay. But they do correspond to points on. So they do correspond to points of an interesting 3D space. That we'll see soon. Don't want to spoil the fun. So this is actually the next section. Okay. One more thing to note. Rotations of S2 don't commute. Not in general, anyway. Okay, you can find some that do, but in general they don't commute. And so an example of this is to consider a quarter turn around the z-axis with a half turn around the x-axis. So consider z sub 1/4, which is a quarter turn about the z-axis, and x sub 1/2, which is a half turn around the x-axis. So a half turn about the x-axis. Okay. So what do we do to see that these things don't commute? Well, the idea is we see where 1, 0, 0 is sent, right? So the front point of the sphere in space. So let's just consider the product of these two things. So let's look at x sub 1/2 z sub 1/4. What does that thing do? So it takes the point 1, 0, 0 and it sends it to, so we're first doing the quarter turn around the z-axis. Okay, so think if I have maybe I'll draw a picture here to remind us, right? So here's x, here's the point 1, 0, 0, our front point. Here's the y-axis, here's the z-axis. So if I do a quarter turn about the z-axis, the point 1, 0, 0 goes over here, right, to 0, 1, 0. Okay. And then the next step in this product of rotations would be the half turn about the x-axis. And so a half turn about the x-axis would take 0, 1, 0 over here, right, to 0, minus 1, 0. Okay, so 0, minus 1, 0. Okay, so then let's see what happens when we do it in the other direction. Okay, so let's start with the same point, 1, 0, 0, and see where this gets sent by a half turn about the x-axis. So we have 1, 0, 0, a half turn about the x-axis sends this where? Well, we're on the x-axis. A half turn about the x-axis, it actually fixes that point. So this gets sent to 1, 0, 0. Oh, now you see what the problem is going to be here, right? So in this way, when I follow it by a quarter turn about the z-axis, I go to 0, 1, 0. So clearly, these are not the same. So these two, this product of rotations does not commute. Okay. All right. Okay. So that's a look at the rotation groups of the sphere. We're going to see, we'll revisit this here in a second after we have a better way of talking about rotations in space in general. And so that better way actually comes from the Quaternions. Okay, and so our next step is to represent space rotations via the Quaternions. So I know I had mentioned the Quaternions previously and even defined them and gave a few properties, but I'm going to go over them again just because they're very important for this, and this is definitely the best way. So this is the most convenient way of doing this, really. So this is the most convenient way of going about this. And it doubles as kind of being like mathematically the most like elegant or like beautiful way of doing this as well. It's a little bit subjective, but it is nonetheless true. Okay. And so, what do I want to say here? So recall a Quaternion had a description using matrices. So a Quaternion is a 2 by 2 matrix. This is one way of thinking about it. So it's a 2 by 2 matrix of the form Q. So I'm going to write it like that. So Q is a matrix that looks like A plus IB in the first slot, C plus ID in the second slot, minus C plus ID in the third slot, and A minus IB in the fourth slot. Okay, where A, B, C, D are all real numbers, and I is the imaginary unit. So I squared is minus 1, right? So I is the square root of minus 1. Okay. Now, this was the matrix form of this, and there's actually an exercise a couple chapters ago that has you showing that this has all the same properties of the quaternions defined in another way. And so this just for the sake of seeing this in both ways, and I know that I've already written this previously. Another way that you can write out Q is in the form A times 1 plus B times I plus C times J plus D times K, where maybe I should put a little symbol over this one. So where 1 is the 2 by 2 identity. So 1 is the 2 by 2 identity. I is the matrix that is I times the identity, except it's conjugated in this last slot, so it's a little different, but that's how I always thought of it. J is 0, 1, minus 1, 0. And K is 0, I, 0. Okay. And so I had listed what some of these products are. You can work these out using matrix multiplication. But for instance, I times J using matrix multiplication is seen to be K, which is seen to be the same thing as minus J times I. Okay, and if you multiply I by itself, you get minus 1, where 1 is that identity matrix. So it's minus the identity. Okay. So, since Q, a generic quaternion, corresponds to a quadruple of real numbers, A, B, C, D, we think of the quaternions we think of a quaternion as being a point in R4. We think of Q as a point in R4. Okay. All right, so now I'm going to define a few things here happening in R4. So if P is a point in R4, it's just some generic point in R4, we're not necessarily thinking about a quaternion here, then the map that takes a point P and sends it to the point PQ, where you've multiplied by the quaternion on the right here, okay, multiplies all distances in R4 by the length of Q, that is the distance of Q thought of as a point in R4 to the origin. Okay, so this is the distance of Q from the origin. The origin in R4. Okay. Why is this the case? Well, note that if you look at the determinant of Q, determinant of a 2 by 2 is this entry times this entry minus this entry times that entry, right? Which, if you work out algebraically what you get when you do that, these minus signs and this I work out perfectly so that what you get here is a squared plus b squared plus c squared plus d squared, which is exactly this length of Q. Okay, sorry, length of Q squared, because there's no square root here. Okay. But then, where we get that this map multiplies all distances in R4 is from the following. If I consider the length of the point PQ squared, that is the determinant of PQ, right, thought of as a matrix in this way, which is, remember the multiplicativity property of the determinant, so this is the same thing as the product of those determinants. Okay, but the determinant of P is just length of P squared, and determinant of Q is also length of Q squared. Okay, thus, the length of PQ is the length of P times the length of Q. And so if you began with P and you got sent to PQ, when you took the length of that vector or the distance from that point to the origin, what you get is the same distance you originally started with, length of P, times length Q. Okay, so that's why that is. Okay, and in fact, from that we can just write out exactly this. So if P1 and P2 are 2 points in R4, then the distance from, say, P1Q to P2Q is equal to the length of P1 minus P2 times Q. I'm just factoring out there, right, which of course is the length of P1 minus P2 times the length of Q. And so this tells you that all distances are multiplied by length of Q. Okay. Thus, if the length of Q is 1, the map that sends a point P to the point PQ is an isometry. This is why we cared about showing that it scaled the distances in a very predictable way. Right? And so if you were judicious in picking the quaternions that you're talking about here, this map in question is actually an isometry, because the length of the image points, or the distance between the image points, would just be the distance between the points. Okay. So, I mean, what this statement literally says is thus the distance between P1 and P2 is multiplied by length Q. Okay. All right. Now, the map that sends a point to QP is also an isometry when the length of Q is equal to 1. Now, you might be a little bit confused here, because I looked at both of these, and you say, well, aren't these the same maps? But they're not, right? They're not the same maps, because recall that the Quaternions are not commutative with respect to multiplication. I'm not going to write that out, but multiplication of the Quaternions is not commutative, right? It's actually one of the things that the Quaternions, that was noticed about the Quaternions, is that they're the multiplication in them is not commutative. Okay. All right. And so it's true for both of these maps that we get isometries in these cases. Okay. So what are we doing here? What is the purpose of any of this? Okay. It turns out these are extremely useful for studying rotations of R3. And when I say these, I mean these maps. Okay. All right, so that's it. I have like 5 minutes more to say, maybe a little bit more with calculations that need to be done. Let's say maybe 10 minutes more to say on this topic, and then that will be all that we do for Chapter 7, and we will move on. We'll move on to the last bit of this course, which will construct the true, in some sense, the truest example and the best example of non-Euclidean geometry. Okay. So anyway, so that's where we're headed. You might have seen that we haven't had an exam 2. I haven't said anything about it, even though I think technically we are scheduled for an exam 2. I don't think I altered the syllabus yet, so I'll make an announcement soon and post it to Elms about that. So it will be it'll be pretty easy going. Don't panic about it. I will in lieu of an exam 2, there will be some other assignments that won't be too long. It'll be kind of like alternate homework assignments. But anyway, I will let you know about that soon. So anyway, have a good Thanksgiving break, and next lecture will be next Monday. So that's the plan. So I will see you all next Monday.